You're listening to the Bare Metal Cyber Prepcast, created to help you succeed in your educational journey. Learn more at baremetalcyber.com, where additional prepcasts, books, and training materials await. Let's get started. When we talk about artificial intelligence, it is tempting to think of it as a single, monolithic thing. You give it an input and you get back an output. But in reality, most AI systems are better understood as pipelines, structured sequences where information flows through multiple distinct stages before becoming a usable result. A pipeline is much like an assembly line in a factory. Raw material enters at one end, it passes through specialized stations that refine or shape it, and eventually it emerges as a finished product at the other end. In AI, the raw material is data. The stations are processes like pre-processing, modeling, tool calls, and formatting, and the finished product is the answer, prediction, or insight that a user sees. Thinking in terms of pipelines allows us to move beyond the myth of AI as magic and instead understand it as engineering, a process of carefully arranged steps, each of which has a purpose, dependencies, and potential weaknesses. At the foundation of every pipeline lies input data. Whether it is text typed into a chatbot, an image uploaded to a recognition service, audio captured from a microphone, or structured rows in a database, nothing in an AI system happens without data first entering the system. Just as you cannot cook a meal without ingredients, you cannot operate an AI pipeline without data. The quality of this input strongly shapes the quality of the output. Grainy images lead to weaker recognition, poorly transcribed audio leads to less accurate responses, and biased text samples can lead to skewed generations. For this reason, data handling at the entry point is often the most scrutinized and carefully engineered stage. Professionals often remind themselves of the phrase garbage in, garbage out, to emphasize that no model, no matter how advanced, can fully compensate for deeply flawed inputs. Understanding the importance of input data is the first step to seeing why pipelines must be designed holistically rather than piecemeal. Raw data, however, is rarely ready to be consumed by a model. Pre-processing functions are the unsung heroes of the pipeline. Before a model can make sense of words, those words must be tokenized, broken into units the model can represent numerically. Before images can be recognized, they may need to be normalized in size and color. Before structured data can be analyzed, missing values must be handled and formats standardized. Pre-processing is like washing, chopping, and arranging ingredients before cooking. It does not make the final dish, but without it, the cooking process would fail or produce wildly inconsistent results. Normalization ensures values are comparable, cleaning removes noise and errors, and tokenization transforms language into a form the model can interpret. These processes may seem mundane compared to the model's predictions, but they are essential for reliability. In fact, many production failures trace back not to the model itself, but to inconsistent or poorly designed pre-processing steps. The centerpiece of the pipeline is the model itself. This is the component that has learned from training data how to recognize patterns, generalize from past examples, and generate new outputs. The model is often celebrated as the brain of the system, but it is only one part of the larger whole. In practice, the model sits like a specialized engine in a larger machine. It accepts processed inputs and transforms them into predictions, embeddings, or generative outputs. The sophistication of the model can vary widely, from a relatively simple logistic regression for predicting probabilities to a massive transformer architecture that can produce human-like text. Regardless of scale, the model's role is always the same. It is the trained mechanism that converts inputs into signals that the rest of the pipeline can act upon. Thinking of the model as a processor, not the whole system, helps demystify AI and highlights the importance of the stages surrounding it. It is also critical to distinguish between training and inference when talking about the model. Training is the process of building the model, where it is exposed to large volumes of data and adjusts its internal parameters to learn patterns. Inference, on the other hand, is the application of that trained model to new data, the process that runs each time you type a question into a chatbot, or upload an image for classification. This distinction is like the difference between teaching a student over years of schooling and asking that student to answer a question on an exam. The training phase is costly, time-consuming, and rarely repeated in day-to-day use, while inference is rapid, repeated millions of times in deployed systems. Keeping training and inference separate in your mental model of the pipeline helps you understand why companies invest heavily in training once, but then optimize inference constantly for cost and speed. Modern pipelines rarely stop at the model stage. Increasingly, they integrate external tools to extend the model's capabilities. These tools might include retrieval systems that fetch documents from a database, calculators that ensure numerical accuracy, or APIs that connect the model's output to external services. Tool integration is like allowing the brain in our analogy to consult a library, a calculator, or a colleague. It extends what the model can do without requiring it to memorize everything or solve every type of problem from scratch. For example, a language model asked about the weather might query a weather API rather than attempting to generate a forecast from its training data. Tool use represents one of the most powerful trends in modern AI. Models are no longer isolated engines but orchestrators of broader systems. Of course, pipelines need decision and control flows to manage complexity. When should a retrieval tool be called? When should the model's output be used directly versus routed through another process? Logic layers within the pipeline handle these questions. They act like traffic signals at intersections, directing the flow of inputs and outputs depending on conditions. Sometimes this control flow is simple, such as always using a retrieval step. Other times it is complex, involving conditions, thresholds, or fallback strategies. Designing these decision layers is both a technical and philosophical task. Do you prioritize speed, accuracy, or cost? Each choice shapes the pipeline's behavior. By including control flow, pipelines become dynamic systems rather than rigid chains, adapting to input types and system goals. Once a model produces an output, that output often needs formatting before it becomes usable for the end user. Raw logits, the unprocessed scores a model generates, are meaningless to most people. Instead, they are transformed into structured results, probabilities, or human-readable text. Output formatting is the stage where the system's results are molded into forms that align with user expectations. For example, a chatbot might wrap a generated answer in clear sentences, while a classification system might present percentages with confidence intervals. This stage is crucial because it shapes not only usability but also trust. Poorly formatted outputs can confuse or mislead, even if the underlying model performed well. Effective formatting is about communication, turning the technical product of the model into something understandable and actionable for the human recipient. At the end of the pipeline sits the user experience layer. This is the interface where people interact with the system, whether through chat windows, dashboards, voice assistants, or embedded widgets inside larger applications. The user experience is not simply a cosmetic wrapper, but an essential stage of the pipeline. It determines how accessible, intuitive, and effective the system feels to the person using it. Two systems with identical models and tools can feel radically different, depending on how the interface is designed. A clunky, confusing UI can undermine even the best AI, while a clear, responsive interface can elevate a modest model into something that feels powerful and user-friendly. In this way, the user experience is both the final stage of the pipeline and the lens through which all earlier stages are judged. One of the most fascinating aspects of modern AI pipelines is the presence of feedback loops. Unlike static assembly lines, these systems often capture user interactions, outcomes, and corrections to improve performance over time. If a user rephrases a query or flags an error, that signal can feed back into the system to retrain models, refine pre-processing, or adjust control flow. Feedback loops are what make AI systems adaptive. They ensure that errors do not merely accumulate, but instead become opportunities for growth. In some contexts, such as recommender systems, feedback loops can be explicit, as when users click like or dislike. In others, they may be implicit, as when engagement time is measured to infer satisfaction. Either way, the pipeline is not a one-way street but a cycle, constantly learning from its own outcomes. To ensure these feedback loops and other stages remain reliable, pipelines incorporate monitoring components. Monitoring is the practice of watching for errors, drift, bias, or degradation over time. For example, a language model may perform well when deployed but gradually drift as the world changes and its training data becomes outdated. Monitoring can catch these issues by comparing outputs against benchmarks or detecting unusual patterns. It is like a quality control station in a factory, checking each product as it leaves the line to ensure it meets standards. Without monitoring, pipelines risk becoming brittle, delivering outputs that are increasingly misaligned with reality while operators remain unaware. Continuous monitoring ensures resilience and trustworthiness over the lifecycle of the system. Security is another essential layer in pipeline design. Each stage introduces potential vulnerabilities. Raw data may expose sensitive information, pre-processing might fail to filter malicious inputs, tools might be exploited to leak information, and interfaces may expose outputs to misuse. Thinking about pipeline security means recognizing that risk is not confined to the model but distributed across every stage. For example, a malicious actor might inject poisoned data into the pre-processing stage or exploit an API in the tool integration step. By acknowledging these risks, designers can implement safeguards at each stage: encryption for data, validation checks for pre-processing, access controls for tools, and auditing for user interactions. Security becomes not a bolt-on afterthought, but a thread woven through the pipeline. As pipelines scale to serve millions of users, they encounter new challenges in performance, latency, and cost efficiency. What works smoothly for a handful of queries may buckle under heavy load. Scalability requires careful attention to each stage. Pre-processing must be distributed, models must be optimized for inference speed, tools must handle parallel requests, and interfaces must remain responsive. The challenge is much like running a restaurant. It is one thing to cook dinner for a family, but quite another to serve hundreds of customers at once. Scalability concerns force designers to confront trade-offs, balancing quality of results with resource limits and costs. This makes scalability not a technical afterthought but a core design principle of pipelines. Finally, pipeline design is never complete at launch. Life cycles matter. From the moment a pipeline is deployed, it enters a phase of ongoing maintenance, evaluation, and evolution. Models may need retraining, pre-processing may need updating as new data formats arise, and interfaces may need redesign to meet user expectations. The pipeline is a living system, much like an organization itself. It must adapt or risk becoming obsolete. Lifecycle integration ensures that pipelines are built with mechanisms for versioning, testing, and iteration, not as one-off projects. By seeing pipelines as evolving entities, professionals prepare themselves for the reality of continuous improvement rather than static perfection. To close Part 1, let us consider a vendor-neutral example that illustrates the concepts covered so far. Imagine a text-based system where a user types a question. The text is first pre-processed, tokenized, and normalized. It then enters a model that generates an initial response. The system consults a retrieval tool to fetch relevant documents, incorporates that knowledge, and produces a final answer. This output is formatted into coherent sentences, displayed in a user-friendly chat window, and captured in logs for monitoring. Feedback from the user, perhaps a thumbs up or down, informs future refinements. At each stage, security measures, monitoring, and scaling strategies play a role. This simple, generic workflow, input, pre-processing, model, tools, formatting, interface, feedback, captures the essence of AI as a pipeline. For more cyber-related content and books, please check out cyberauthor.me. Also, there are other prepcasts on cybersecurity and more at baremetalcyber.com. One of the core engineering principles of pipeline design is the separation of concerns. This principle means that each stage of the pipeline has a distinct role and responsibility, isolated from the others as much as possible. Imagine a restaurant kitchen. The chef cooking entrees, the pastry chef making desserts, and the dishwasher cleaning utensils all operate independently but contribute to the same meal service. If one person had to do everything, efficiency would collapse and quality would suffer. Similarly, in AI pipelines, separation of concerns allows pre-processing, modeling, tool integration, and user experience to evolve independently. If a new pre-processing algorithm becomes available, it can be swapped in without redesigning the entire pipeline. If a more efficient model is trained, it can replace the existing one without forcing changes in the interface. This modularity keeps systems flexible, easier to maintain, and more resilient to technological change. Alongside separation of concerns is the concept of interoperability across components. For a pipeline to function smoothly, each stage must not only be effective in itself, but also communicate seamlessly with the others. This requires adherence to standards for data exchange, formats, and protocols. Think of an international airport where flights from different airlines and countries all need to use the same runways, terminals, and baggage systems. Without common standards, chaos would ensue. In AI pipelines, interoperability ensures that a tokenized dataset can be ingested by the model, that the model's outputs can be passed into external tools, and that formatted results can be displayed in user interfaces. Without this interoperability, even a highly advanced model can become unusable if it cannot speak the same language as the surrounding system. Error handling is another indispensable dimension of pipeline design. No model, no tool, and no data source operates with perfect reliability. Failures are inevitable, and the question is not whether they will occur, but how gracefully the system will handle them. Robust pipelines include fallback mechanisms. If a retrieval tool fails, the system might default to a model-only response. If pre-processing encounters unexpected characters, it may substitute neutral tokens rather than crashing. These mechanisms are like airbags in cars. You hope never to need them, but when accidents happen, they reduce harm and preserve continuity. Without proper error handling, an entire pipeline can collapse from a small, localized failure. With it, pipelines can degrade gracefully, preserving user trust even when imperfections occur. Observability is the discipline of making pipelines visible to their operators. Just as a pilot relies on dashboards, dials, and indicators to understand the status of an airplane in flight, pipeline operators rely on logging, tracing, and metrics to understand how each stage is performing. Logs capture what happened step by step, tracing shows how inputs flow through the system, and metrics provide quantitative measures such as latency, error rates, and throughput. Without observability, pipelines become black boxes, leaving operators guessing when things go wrong. With observability, issues can be diagnosed, trends tracked, and improvements verified. In practice, observability transforms pipeline management from reactive firefighting to proactive optimization, enabling continuous improvement and safer scaling. In some pipelines, human in-the-loop placement is a critical design choice. While automation drives efficiency, there are times when human oversight is essential for quality or safety. For example, in medical diagnosis systems, a model's suggestion may pass through a human clinician for review before being delivered to the patient. In legal contexts, AI-generated drafts might require attorney approval before filing. These checkpoints allow humans to correct errors, apply judgment, and provide accountability. Designing where and how humans intervene is not trivial. Too many checkpoints slow the pipeline. Too few risk unchecked errors. The art lies in placing human oversight where it provides the most value, at moments of high uncertainty, high risk, or ethical sensitivity. In doing so, pipelines balance efficiency with responsibility. Automation, however, remains the lifeblood of pipelines. Orchestration systems, schedulers, and workflow managers reduce manual effort by ensuring that tasks move from one stage to another without constant human intervention. Just as modern factories rely on conveyor belts and robotics to keep production lines running, AI pipelines rely on automated orchestration tools to coordinate pre-processing jobs, model inference, tool queries, and output formatting. Automation ensures that systems can operate at scale, running thousands or millions of tasks without bottlenecks. It also reduces human error, since machines are less likely to forget steps or missequence actions. Automation does not eliminate human roles, but shifts them from repetitive tasks to oversight and improvement, raising the overall efficiency of the pipeline. Evaluation hooks are built into pipelines to ensure ongoing measurement of quality. These hooks might involve periodically checking model outputs against known benchmarks, sampling user interactions for correctness, or monitoring error rates over time. They serve as diagnostic stations within the pipeline, similar to weigh stations along highways where trucks are checked for compliance. By embedding evaluation directly into the pipeline, operators ensure that issues are caught early rather than only during major reviews. For instance, if accuracy suddenly drops after a pre-processing update, evaluation hooks can detect the shift immediately, allowing rollback before users are widely impacted. Without these hooks, performance degradation might remain hidden until users complain, at which point trust and reputation may already be damaged. Ethical and governance hooks extend this principle beyond technical quality to issues of fairness, privacy, and compliance. Pipelines that handle personal data may need explicit checkpoints for anonymization. Systems that make sensitive decisions may include bias detection layers to flag disproportionate impacts. Compliance requirements such as data residency or logging regulations can be enforced through policy-driven hooks. These elements are like guardrails on a mountain road. They may not be needed every moment, but when risks arise, they prevent catastrophic outcomes. Including governance hooks within the pipeline ensures that ethical and legal standards are baked into operation rather than retrofitted as afterthoughts. This approach recognizes that advanced AI is not only a technical challenge but also a societal responsibility. Resilience and fault tolerance are hallmarks of mature pipelines. These qualities describe a system's ability to withstand failures without collapsing. In practice, this may involve redundant servers, replicated data stores, or multiple models serving as backups for one another. The principle is akin to designing bridges with multiple supporting cables. If one cable snaps, the bridge still stands. Fault-tolerant pipelines degrade gracefully rather than failing catastrophically. For example, if one model endpoint becomes unavailable, the system may automatically reroute queries to another. This resilience is particularly important at scale, where failures are not rare events but statistical certainties. By designing for resilience, operators ensure continuity of service even in the face of inevitable breakdowns. Adaptability and evolution are equally critical. Unlike static software systems, AI pipelines are built for continuous change. New models are trained, new tools are developed, new data sources emerge, and user expectations shift. A rigid pipeline quickly becomes obsolete. Advanced pipelines are designed with flexibility, allowing components to be swapped, retrained, or reconfigured without massive rewrites. This adaptability mirrors biological systems. Species that evolve survive, while those that do not perish. In the same way, pipelines must evolve with the technological ecosystem, staying relevant through iterative improvement. Adaptability is not just a feature, but a survival trait in the fast-moving world of AI. Yet with all these capabilities, pipelines also embody trade-offs in complexity. A richer pipeline with multiple tools, feedback loops, and governance layers may produce higher quality results, but it also demands more oversight, incurs higher costs, and becomes harder to debug. Simpler pipelines are easier to maintain, but may lack flexibility and depth. Professionals must navigate these trade-offs based on context. A medical pipeline may justify high complexity for safety, while a customer support chatbot may prioritize simplicity for cost-effectiveness. Recognizing these trade-offs prevents the naive assumption that more is always better and fosters mature decision-making in pipeline design. On an industry-wide level, pipelines define modern AI products more than individual models. A cutting-edge model is impressive, but without a pipeline around it, Pre-processing, tool integration, monitoring, and user experience. It is like an engine sitting idle in a garage. Pipelines are the vehicles that carry models into the real world, making them accessible, reliable, and safe for users. Companies that excel at pipeline integration, not just model training, are those that succeed in delivering AI at scale. This insight reshapes how we think of AI leadership. It is not the best single model that wins, but the best designed pipeline. To understand pipelines more fully, it helps to compare them with traditional software pipelines. In software engineering, build and deployment pipelines ensure that code moves from development through testing to production. These pipelines emphasize reliability, version control, and automation. AI pipelines share these qualities but add unique challenges, such as handling non-deterministic outputs, monitoring for bias, and retraining models with new data. The similarity lies in the flow of tasks. The difference lies in the unpredictability and ethical stakes of AI. By framing AI pipelines as cousins of software pipelines, learners can build on familiar concepts while appreciating the added complexities AI introduces. In enterprise contexts, pipelines become central to integrating AI into core business processes. Banks rely on pipelines for fraud detection, retailers for recommendation systems, hospitals for diagnostic support, and governments for data analysis. In each case, the pipeline is what makes AI operational rather than experimental. Understanding pipelines, therefore, becomes essential not only for engineers, but for decision-makers across industries. Knowing how data flows, where risks lie, and how outcomes are shaped empowers leaders to make informed choices about adoption, investment, and governance. Pipelines, in short, are the backbone of AI in enterprise. As this episode closes, it prepares us for the discussions ahead on scaling laws and training dynamics. Pipelines are the stage on which those dynamics play out. Understanding how data flows through pre-processing, modeling, tools, and interfaces provides the groundwork for grasping why scaling changes outcomes, why training requires certain resources, and how operational choices shape results. By mastering the concept of pipelines, you equip yourself with the mental model needed to approach all subsequent topics in the series with confidence. In conclusion, this episode has shown that AI systems are best understood not as single units, but as pipelines, where data flows through pre-processing, models, tools, and interfaces, with monitoring, feedback, and governance at every stage. These pipelines embody modularity, interoperability, resilience, and adaptability, while balancing trade-offs in complexity and cost. More than just technical constructs, they represent the organizational and ethical frameworks that bring AI into practical reality. With this foundation in place, we are now ready to turn to the next layer of understanding: how scaling laws and training dynamics shape the behavior and performance of the models at the core of these pipelines. Thanks for tuning in to the Bare Metal Cyber Prepcast, your trusted source for cybersecurity news and insights. Remember to subscribe at baremetalcyber.com so you never miss an update. And visit cyberauthor.me for best-selling cybersecurity books that equip you with expert knowledge. Until next time, stay secure and stay vigilant.